Ladies and gentlemen, welcome to the Thunderdome Debate Night. That's right. If you can believe it, nobody wanted to buy the pay-per-view rights to this debate tonight, but I think they're crazy for that. Instead, you can only enjoy it live here in person. This is technically a very exclusive event because no one else is going to get to see it except for you. What we have here tonight is a fantastic group. They are going to be debating on the merits of adiabatic versus isothermal humidification. Now, you're probably asking a couple things. First of all, Doug, what's up with this AI-generated image on the screen?
I love it.
And why is Riz specifically in the middle? Now, look, I spent more time on the debate questions than the AI generation, if I'm being honest. But if anything can be proven, AI can't be trusted. Trust the experts. These guys are the experts in their field, and they're all going to spend approximately about a minute introducing themselves. But before we get into that, I just wanted to explain the general layout. There's going to be 4 key questions for this event this evening. They're each going to take time to respond. The other team will have a moment to, or about a minute or so if they have any rebuttals. But most importantly, more than anything else, to make this the interesting debate it's meant to be, these teams are going to represent their sides as if it's the only right solution in the world. They are going to attack the opposition in a way that makes debates what they truly are, which is interesting. So put on your bias caps, get ready to root for your favorites, and I'll make one more announcement just before we truly get into it. We did have one of the people who's going to be the speaker tonight on the Isothermal team, Duncan Kerr from Dry Steam. So unfortunately, he couldn't make it tonight. He got the flu, so either one of 2 things is true. Either 1, he is very sick and hope he's feeling better, or 2, he's very committed to how important humidification is for keeping pathogens at bay. I mean, you know, that's respect. Shout out to Duncan. So we've got Mo Saka here from HTS. If you're wondering, did Doug bully him into it because we're in the same company? Unrelated. Not but thank you both for being here tonight. Big round of applause for both for stepping up. So, just to get started, we'll have the team introduce themselves. We'll start with the group on my left. Nick, if you want to, go ahead.
Yeah, thanks, Doug. Hi, everyone. My name is Nick Lee. I'm head of product and sales support at Condair, a humidity control manufacturer. I've been about 19 years in the humidity control industry, working very closely on both sides of the debate here on steam and adiabatic. Excited to represent Team Adiabatic tonight. We've seen some really cool projects with these systems in the last couple of years, and I'm hoping to share some of that with you tonight.
My name is Doug Harris-Lowe with Kilmer Environmental. I'm a technical sales rep out of the Mississauga office. We're a manufacturer's rep for a number of different industry-leading products, including humidification products from Condair. I've been in the industry for 9 years now and excited to be debating tonight.
My name is Kurt Pajero with Smith Manson Consulting Engineering, and I work in a lot of labs and healthcare buildings, and been around in the industry longer than I like to.
Testing. Mo Saka from HTS. As you guys heard, I got called in 30 minutes ago, or an hour and a half ago now, to join in. Good news is I've been solving HVAC problems and designing systems for the last decade and a half, so I think I'm up for the task.
Hello everyone, I'm Matthew Reed. I'm the Technical Director of the Heating Department for ASHRAE. I've been working with boilers for 24 years, which I know is probably shocking a lot of you out there because I look so young, or at least I used to a couple of years ago. But to be truthful, when I was signed up for this, I had never even heard of adiabatic humidification before, and then once I dug into it, I decided, why would anybody ever talk about this? It's ridiculous.
That's the right energy.
Hello everyone, I'm Reza Sultani with Spark Sarco. Whenever there's a steam, there's Spark Sarco. So we go working on pharma projects, food projects, healthcare projects, and healthcare is the reason I'm here to defend steam and make you fall in love with steam. I've been with Sparks for 5 years. Before that, I did hydronics, and before that, I did air distribution at ASHRAE. Started to come to ASHRAE sessions 10 years ago, and I love it to be up here to discuss steam, specifically in healthcare.
We know that not everyone in here is by any means a humidification expert, but today you can pretend to be. We have our friend Nick here who's going to just lay out some key terminology to kind of just make everybody have a base level understanding of what we're all talking about here.
Sure, thanks. So one of the most exciting things tonight is that we're talking about humidification. A lot of times this is left out of buildings or value engineered out. There's a lot of great reasons we shouldn't do that. I'm sure we'll cover some of them here tonight. But when we're talking isothermal, or more traditionally known as steam, versus adiabatic, or a kind of direct air to water type system, we're really talking about two different processes on the psychrometric chart. With a steam type system, you're adding moisture directly to the air, increasing the humidity. We're going to represent that typically as a vertical line on the psychrometric chart. One of the really neat things about adiabatic, though, is that we're drawing that energy we need to convert the liquid water to gas from the air itself. And so as a result of that, we're going to get evaporative cooling. And that we represent as a line that moves upwards and to the left on the chart. Probably most easily understood by that feeling you get when you get out of a pool or a lake or a river and you immediately start to feel cold. That's the evaporative cooling effect acting directly on your body. And that's what we see here represented on the chart.
Great, and thank you for saying that. So now, with that aside, we're going to get into the questions this evening. And just because I think I ordered the slides this way, I'm going to ask you guys first, Team Adiabatic. In terms of a cost perspective, for your system, what are the main installed cost drivers, the main operating cost drivers, and why is yours a better system?
Generally speaking, Adiabatic is going to be the more costly upfront system on an install base from your upfront costs. We've got some slides coming up there, Doug.
Yeah, what are you looking for?
Yeah, we'll start with this one. I'll go to the next one. I changed my mind.
You can't do this to me right now. This one here?
That's the one. That's the one.
Okay, great.
So yeah, it really does depend on which system. There's a number of different technologies when we're talking about adiabatic, a mix of in-the-air handler and duct, some direct in space. Certain systems are more scalable than others, so it really does depend what your install costs are going to be based on which system you're going for the different application. But the real trade-off there is with the energy costs, and that's where adiabatic really wins. An isothermal system, because we're taking in domestic cold water, first you need to heat that all the way up to your 212 Fahrenheit, and then the real energy hog comes from, it takes roughly 1,000 BTUs for every pound of water to convert that into steam. So when we're talking about electrical energy or gas, the costs really add up quickly. So next slide, please. So this is just an example from a case study comparing a couple different technologies. So we've got the hybrid fogging system, which is an adiabatic system, comparing it to gas-fired or electric. This is looking at the system as a whole, and you're looking at kind of the drastic changes in the spikes here. A lot of that is coming from your adiabatic cooling effect. Because now not only are we spending a fraction of the energy to humidify the air itself, but we're taking away some of the energy costs of the cooling system. And I can see the isothermal team over there licking their lips, getting ready to ask the question. And I know I'm anticipating what they're going to say, and they're going to say, well, hey, we're in Ontario here. We're generally heating as we're humidifying at the same time. And while we're talking about our design winter day, that is generally true. But look at the trends in the industry going on as well right now. We've got buildings are being built with much higher R values for the building envelope. We got tighter buildings, so we have a lot less infiltration to worry about. Even advanced filtration methods, so now we're able to reduce our fresh air loads, so heating loads are going down. And I'll remind that we're not just talking about our design winter day, but even the shoulder seasons, there is a lot of times that we're spending in the right bin hours where we are going to have that overlap.
Sorry, was that next slide?
Yeah, this keep going to bin hours.
Oh yeah, can we show the bin hour slide?
Yes.
Yeah, sorry, we're a little out of order here, but...
The last, okay.
There we go.
That one right there, okay.
Yeah. So this kind of highlights what bin hours and what conditions outside where the adiabatic cooling makes sense. And with in our climate here, there is a lot of time spent in the shoulder seasons that we're going to have that overlap. And like I said, that's only going to continue to go in our favor as we tighten up our buildings and increase the R values.
Doug, that was a tight 3 minutes on point. I'm very impressed.
I know it doesn't surprise me.
Yeah. All right. Doug's a nice guy, but let's see, does the Isothermal team have anything they'd like to say in rebuttal?
Very good points. Thanks so much for actually starting with the psychometrics. We didn't get kind of a start of 2.5 minutes start.
A mission statement of what your team's all about.
Okay.
Is that what you're asking about? Yes.
Yes. Are we starting with that, or I'm going into cost?
Why don't you do the rebuttal on this one, and then I'll let you have the 2.5 minutes, or we can inversion
It's okay, actually.
it. By the way, these guys are in fault. I'm just a bad moderator. They were supposed to have 2.5 minutes with the opening statement.
Biased.
I didn't have much on you dinner, guys. I'm not gonna lie.
So are we doing the opening statement?
Go for it. Yes, I'm pretty
Okay,
good.
let's do that.
Sorry.
Okay, as for the opening statement, we put together,
Yeah, so we put together a top 10 list of reasons to go with steam over adiabatic or isothermal over adiabatic. And we're going to kind of break this in half between myself and my partner here. We're going to start off with a big one, and it really should end this before we get too deep into it, but we're going to give you the benefit of the doubt and assume that you have something to say over there. When it comes to isothermal humidification, it's like saying it's finally a type of humidification that won't make you sick and kill you. But again, we'll see how far we get down this road here. There's a lot of misconceptions with the complexity that is going to need to be taken into consideration with regards to the water quality for a steam boiler, and there's even more complexity that's going to be required for the adiabatic system. Again, because we don't want to make you sick and kill you. But we're going to see again how this all kind of unravels. With the adiabatic system, we definitely have some delays with regards to how the system operates to begin with. It's not the fastest to respond, nor is it the most accurate. Unlike where your isothermal system, you can get that humidification within 1% pretty much instantaneously. As soon as there's the call for what you need, you get that. And what a fantastic idea, getting what you ask for, when you ask for it. I know it sounds crazy to that side, but I promise you it exists and it works.
This is exactly the energy I wanted tonight.
You told me, so I'm bringing it.
I love it.
We also have predictability with our isothermal systems. Our steam you can always count on for that slight, 0.5% heat gain in the system, where we are not going to be taking away that heat that we so desperately need in the winter so that we don't freeze you to death and kill you. Although there is some maintenance that is going to be required for your isothermal system, no one's saying that any system is going to be maintenance free. We'd be ridiculous to say something like that. But what we are saying is that the maintenance on our isothermal systems is quite basic and standard. Not to mention the fact that we've been working with steam boiler systems since proper steam boiler systems since the 1800s. We have hundreds of years of experience with this, so it's not like it's anything new for anybody to learn. Unlike the other side.
All right, Matt. You are doing a good job of dunking, but I'm just going to have to give you one more minute, okay?
Yep. And finally, we have the ability to heat recover in a lot of isothermal systems, so we're going to be keeping that one in mind.
okay, so size matters. Steam can be used in large systems and small systems.
Why did you look at me when you said size matters?
We cannot do that with adiabatic. Size matters number 2. Non-wetting distances are major requirements for adiabatic. You need a studio for each air handling unit. Size matters number 3. Coastal wet sections are huge.
And the final dirty little secret with isothermal versus adiabatic, with isothermal you keep your money from going down the drain. Adiabatic, generally only has about a 70% evaporation efficiency, not to mention the 45% loss with the first osmosis. So again, whenever you're ready.
All right, yeah, let's give it a chance. Sorry, guys. Would you like your opening statements now? We've already gone.
Okay, lots of fun. Size matters for sure, especially when we talk about big buildings that have large loads and capacities. And really, you know, when you're getting above 250, 500 pounds an hour, your energy cost and your energy input is really not the type of service you want to be putting into that type of building. Adiabatic really shines, especially in these larger applications when we're getting industrial. One of the really neat things about Adiabatic is we're getting cooling at the same time. Think of your industrial applications, think of any application where you have excess heat in the building, data centers, healthcare. There's a lot of great ways where you can take advantage of that heat, apply that to the conversion of water from liquid to gas, and really get kind of a free lunch on humidifying and controlling the humidity in our buildings. Who's here?
Just jump in. I think one point, the reason why we're here, we have this debate is because climate change is killing us, right? And so steam, I don't know, steam, I've never seen anyone burned by water spray, but it has happened with steam. So that's the other thing I would say. So we're trying to figure out how to decarbonize.
Did you guys pay to cut his mic? That's pretty good.
So I think we're trying to decarbonize, and that's probably the biggest thing that the other side doesn't want us talking about, right? And so that is, adiabatic is the way forward. So you talked about steam systems being around forever. Well, we've gotten in this mess by using the same technology we've used forever, and we have to go in a different direction. There are lessons that have been learned with using adiabatic, and we will admit to that, and we've gotten better. The technology that we have available today, the sensors that we have available today, the cost of that has gone down. So now we're able to implement this technology to kind of make it safer and not get killed by steam.
Alrighty. Oh, Doug,
The size of your energy bill matters too, just to throw that out there.
Wow. Doug was waiting for that one. All right. So,
A quick one for Kurt. Are you going to drink RO water today as part of your sleight of hand there?
I love where this energy is going, guys. This is good for tonight. All right, so just to throw it back to the Isothermal team and bring things back on track when I derailed it, which was a test you all passed. The first question was regarding cost. Why is Isothermal a superior system in terms of cost, both on the capital and operating side? I'll allow the time to include any rebuttals you may want to mention before.
100%. Can we have the first slide, please?
Yeah.
Oh, you got it?
You want to do it for him just because you.
Just let me know.
Yeah.
That's it, yes. So I wanted to start with a comparison of energy consumption. I'm quite surprised that we are hearing that Adiabatic uses less energy. When you get into psychometric physics, it doesn't basically put any difference for Adiabatic versus steam. I did a quick case study for 3 cold months, December, January, and February for Toronto. Average temperatures, average relative humidity. And each two stack, one on the left side is for steam, on the right one without the orange section is for Adiabatic. And you see that the height, vertical axis is all the same. So in reality, without any marketing, Adiabatic and steam, they use the same amount of energy. It doesn't matter what technology you use. So that's basically I wanted to start with that. Now, when we are considering the central energy systems, and if we assume that the boilers are gas-burning boilers, so average 95% of the cost of operation in terms of steam would be for fuel gases. So obviously, I am with everyone in this room. We have to do anything we can do to make the old steam designs, which we can still see on the schematics, very much more efficient than 1900s. It's not that us suppliers do not push it. It's that it has to be shown on the schematics. Can we go to the next slide? We can skip that. Yes. So in terms of cost of capital costs, obviously Adiabatic has more capital costs. Now we have to accept that one of the main applications that we are all here for the debate is healthcare, and healthcare is one of the utmost important. It has the utmost importance when it comes to quality of air quality. So for a new hospital, I've been talking to some estimators for a new hospital. If you compare the concept of adiabatic from the generation standpoint with steam, it's almost same. RO, skid, treatment, pumps, all of that. It would be almost same with the boiler and distribution system in case of steam. So the difference boils down to cost of air handling unit difference. And for a new hospital, the difference in cost could be double-digit millions, which could be used in basically using much more efficient generation systems for steam. We don't need to change the outcome, we just need to basically change the source. Now,
You got about 15 seconds left.
15 seconds. Here we are talking about the cost of absorption. Adiabatic system does not have a very nice absorption efficiency. If you're in a hot and dry place and you want to cool while humidify, then go for it.
All right, minute of rebuttal for the Adiabatic team. I think I'm hearing some good points here. Kurt, what are you going to say about it?
Yeah, I would say, first of all, as far as I'm aware, we don't only heat our buildings for 3 months of the year. So, like, when we look at costs and operating costs and how long we're building, it's not just 3 months. So if I took a snapshot and zoomed in, you might not find something equal, but really the savings are around the shoulder seasons where we do humidify in Canada. We're going to talk about healthcare, it's requirement to humidify in all those months as well. So you're going to see some significant savings there, and that would be even in conventional buildings. And I would say that the other thing is that, you know, when we talk about hot water and generating steam, and you talk about water going down the drain, well, the reality is when you're generating steam, you have lots of blow-down cycles, and you've got hot water going down the drain, and you add cold water to make sure that the hot water isn't too hot when it's going down the drain. And so that's happening all the time too. And the most common steam humidification system I see in buildings is ones that aren't running. And the reason why they're not running is operators are always looking at cost. What's the way to cut costs? Is you shut down a steam humidification system. So that's the most common thing that we see.
Good way to clean up it. That's 1 minute. So we're on to the second question now. That cuts out the first one. This team, Adiabatic went first on the first question, so I will be throwing it over to the Isothermal to start the second question. So, when it comes to long-term maintenance, why are isothermal systems superior to adiabatic?
Isothermal systems will outlive me, and I don't live that tremendously hard of a lifestyle. I live a pretty hard lifestyle. Let's not kid ourselves, but I don't go out, every single weekend. But there is a tremendous amount of truth that most people in this room, if you've been in a mechanical room and you've seen one of those beautiful old school boilers that the gentleman across the aisle says that they turn off for no good reason. You know that these boilers have been there for a very long time. They continue to be there for a very long time. They have an extremely long lifespan, provided that they are maintained. And the maintenance on them isn't overly complex, and let's kind of dive into that, and I can also address some of the points as well. When you're on with an isothermal system, you are going to want to blow down that system. Absolutely correct. You are correct with that one. You are going to have some chemicals in that water that are going to build up, and we're going to want to blow those down the drain because you don't want that scum to kind of build up on the inside of that, on the inside of the boiler or the heat or the steam generator. That can cause us, degradation down the road. However, there's nothing to say that we can't heat recovery from that blowdown, which doesn't mean necessarily that we're always heating it from that 40 degrees to that 212. Usually, there's a whole lot more to that heat recovery side of the steam system, where we can capture a lot of heat from the system itself and the very nature of it, from our flue gases and from our blowdowns. You're also going to have keep an eye on the low water cutoff and the gauge glass to make sure that there's water inside of the system. So, provided that you have a set of eyeballs and looking at the system, I know it sounds complex, but that's a requirement for maintenance on a isothermal system. Plus, there's also the flame inspection. So these are things you're going to be doing every day, having a look at it. If you can look at it, just be like, well, we're not, pouring water over the side of it and everything looks like it's going to be okay. That's step one. You've got that maintenance for it. Monthly, you're going to have a look at your standard controls and your checks and safeties, which is going to be just, are the gauges reading what they should be reading? Can we understand them? Are they covered in grit? Are they flooded? Something like that. And is the valve going to be operating, specifically the relief valve? In a lot of isothermal steam systems, you're going to have a pressure inside of those systems. And the last thing you want is you have any sort of pressure failures. So that's going to be something that you're going to want to keep an eye on. Then your annual inspection, you're going to be cleaning up the entire system. You're taking it apart and giving it a clean. The water side, open up the boiler, check for scale, any debris, stuff like that, give it a clean out. And the fire side, you open up the burner, make sure that you're not sooting up or anything along those lines. If it's an electric side, you're looking at the elements to see if they have any scale on them and whatnot. And again, you're really using your common sense and just your standard methods of maintenance to check these boilers out. Then at the final piece, you're usually doing a little combustion analysis if it's a gas-fired unit, so make sure it's firing as it should. Now,
All right, I got a couple more seconds left here.
now, oh my goodness, that was fast. When we talk about the maintenance of an adiabatic system, we can be talking about a whole lot of minerals inside of our tap water. Now, I know that you're going to have a rebuttal for this one, and I hope you do, because you need a win. I can clearly see it in your face. What I'm getting at here is that for the water that's going to be required for your adiabatic system, you need to constantly be on top of that, make sure it is always at peak performance, where on the isothermal side, it's actually more forgiving than you think.
All right, I think that's a fair amount for time. I'll let you guys respond. I think we're learning Matt drops stacks and likes to parties. That's good to know. Thank you, Matt. Good.
So the maintenance slide, if you please.
Yes. Please feel free to flip
the main thing that you have to remember is that water contains minerals. It's not just pure water. And regardless of which type of system you're using, those minerals need to come out somewhere. With the steam systems, typically we're going to have those come out in the form of scale inside of the tanks and inside of the humidifier. And that's where you're getting involved. Getting your hands in there dirty and direct maintenance. With adiabatic systems, we almost always need treated water. And typically we're going to use reverse osmosis to generate that water. Reverse osmosis can be dedicated to the humidifier. More often than not, it's shared with other functions inside the building. We have a large...
Sorry, you saw it all in order before. I think they decided to jump around.
So we have a large central reverse osmosis system that we're using for other applications in the building as well. Nice thing about reverse osmosis is that it's familiar. It's used across a lot of different applications. There's contractors, there's people that are able to service these. It's not very specialized. When we actually talk about maintenance on the humidifier, because most of the minerals have come out up front, we're really focused more now on maintaining pumps, valves, and checking our spray patterns and nozzles. Again, these are quite common things. There's a lot of contractors that are well versed in maintaining pumps. You find pumps in almost every building. Valves are very much similar. Very easy to get spare parts for those and broadly distributed as well. And the final step is making sure that the water is safe, and that's a topic that they brought up, and it's absolutely true for adiabatic systems, is that we want to make sure that we're maintaining a high level of hygiene and water safety. And this is very similar to what we do in other parts of our buildings as well. It's part of Guideline 12 and ASHRAE 188 that we're sampling, avoiding dead legs, avoiding stagnation, and maintaining water safety within the limits. And we do the exact same things on the adiabatic humidifiers as well. So even though they may seem a little bit foreign when we first started talking about adiabatic humidifiers, it actually breaks down into things we're already doing elsewhere in the building and quite familiar.
Just a quick rebuttal, Matt. I like the way you worded the maintenance. Check the heating elements to see if there is scale. Spoiler alert: if you're not using water treatment, there's scale. I'll save you the trouble.
All right, we pass back over. You guys, we have a little bit of time left, so I'll let you throw one thing in.
Sure. No, I was going to say that the adiabatic system is more maintenance dependent for sure, less than the steam system. And basically, as simple as putting a salt in softener, how many times in hospital we see that's forgotten. So we basically should also consider some human error as well as the machine error when we consider the chance of getting sick and die, right? So that's the...
That's a very interesting comment. I would say, like, the one thing that, dealing and walking to many different buildings and seeing the demographics change with people who maintain buildings, building operators are afraid of steam. Engineers are afraid of designing steam systems. That is the one, they are more nervous about that, and that expertise is slowly leaving our industry.
I don't agree.
And steam is based on, is it like a dinosaur technology, and huge dinosaurs?
Keep it behind the table, Joe.
Dinosaurs to generate steam, right? So
I've never seen someone be so confidently wrong before. Good for you.
All right, we're moving on.
They don't want
That's fundamentally the issue, is that you have a generation of people coming into the industry and they are not familiar with maintaining steam systems, steam traps, and everything else that goes along with it. You might have to have TSSA involved, you've got those high pressures. And so that's the most common thing that we see with steam. They don't know how to maintain steam systems, they're nervous about it, and you've got to keep an eye on them every single day. With RO systems, other than the softener, which is not too hard to deal with, you're not dealing with something that you have to look at as mission critical that you have to pay attention to every single day.
Alrighty. Luckily for you guys, that was the rebuttal period plus everything I allowed. You're very lucky, all of you. So from there, though, we're going to transition to you guys still for the next question. This one is directly related to more of the IEQ aspect. Why is adiabatic superior from environmental and IEQ aspect?
Right, so I think the key thing that we've mentioned about adiabatic is that you do have to focus on water treatment. And so the reputation that we've gotten is that older adiabatic systems, there was a lot of risk over there with those adiabatic systems because there's high rejection rates, there's a lot of water in the system, you could have things that were not great for your health there. But the reality is we need humidification systems in the building. I think I was chatting before, we evolved in the plains of Africa in that environment. The relative humidity was generally pretty high, much higher than it is in North America. So our immune systems over here in the GTA, for instance, are not used to those lower humidity levels in the summertime, in the wintertime. So we need the high humidity levels, and you can get it either way. One thing we do is we clean the water out, get rid of the food in that water by putting in RO water systems. And in that case, when you do that, you reduce the risk of actual bacterial contamination within the water. And then we have ongoing things that we do to improve that as well. So you can have UV on coils, you can have UV on drain pans, on the water treatment itself, and you keep that water moving and you drain things down. Right? So you can manage the risk. The good news now is that the cost of sensors and the cost of BAS monitoring systems and people being able to deal with it is pretty straightforward. And the systems nowadays have built-in safeties. They've all come in package controls. We're not counting on controls contractors coming and figuring it out. Most of the manufacturers today package all those safeties within their controls, similar to what you have in a boiler, so systems shut down if they're no longer safe.
Alright, you guys got actually 1 minute left. You want to add anything to what Kurt said? If not, we'll hand over to Rosa.
No, actually, I think Kurt covered a lot of that pretty well. The one thing that I really would maybe add on is the indoor air quality piece, and that's a piece that's often not talked about enough. There's so many benefits for controlling the humidity in your building, and I think our previous slide there actually showed a few of them. We used to talk about this as a comfort topic or process control topic. It's really a health topic. Maintaining that mid-range 40 to 60% relative humidity has a lot of impacts on how your body deals with viral transmission and reacts to microbial invaders. We need to start changing how we think about humidity control in buildings in general.
All right, thank you. Thanks for coming in under time. I'd like to see that. You guys have a minute for rebuttal now.
Sure, I was going to ask Kurt, I really think you mentioned reduce the risk, not eliminate. So as a patient, if I'm going to a hospital, I want to be 0% chance of getting sick from air ventilation, not a reduced risk. So my perspective on that goes beyond sales for me. If for healthcare, we have to design for patient, not for decarbonization, not for risk management. So when it comes to pharma, when it comes to healthcare, we have to practice design of risk elimination. So I'm not sure if that's considered a rebuttal, but that's what I wanted to share.
What a strong point to say. I'm not sure if facts were a rebuttal. I love that. Sorry, you have a little more time left if you want to say anything. After that, guys,
I think like everything else in life, you manage your risk and the goals are, right? So when we talk about energy efficiency and we talk about decarbonization that's going to come up, that is why we're looking at these technologies, because we're balancing the different risks. The other thing that I'm sure people who generate steam don't know anything about is filtration. We do really good filtration in healthcare. So the reality is we put in MERV 14 filters. and in really in environments like operating rooms that are absolutely critical, we put in HEPA filters. So even if you had a small risk of any microbial growth, that is going to be eliminated. There's also, you eliminate the dose size. So if anything did grow, it's all going through those filters before it goes into any patient care areas, and it's significantly diluted.
All right,
So,
sorry, I apologize. Just for time's sake, that's all great points. Just want to add for the isothermal side, you guys want to build on why it's a superior IEQ system.
Yes, can we go forward?
Yeah, the adiabatic, or sorry, the isothermal slide is closer, further along. Down one.
Keep going.
we put the important slides first.
Okay, so yes, good. So again, we are talking about healthcare a lot, and basically when it comes to Adiabatic, there are several technologies, and when it comes to healthcare, high capacity systems, we are comparing the centralized steam generation and distribution versus high pressure atomized Adiabatic system. So before getting to the details of that, these two studies are the staple studies when it comes to relation of humidity and people dying in healthcare because of bacteria. Imagine you don't have any, you're going to hospital for a reason and you leave with a new bacteria. And every year, 100,000 of people die because of the second-hand bacteria that they basically catch it when they go to the healthcare for a different reason. Now, 10% of patients visiting hospitals, they get sick for different reasons that they visited. So these are results that are published by Harvard Medical School and the University of Chicago. So now we can conclude that humidification in healthcare is very important, much more important than data center or museum, right? Now, there are 5 elements that drive that, making people sick and killing them. One of them is air ventilation and humidification. You can go next. Now, we have a choice to eliminate the risk or to manage it. So if it's me, I would like to eliminate the risk, and that's true boiling. True boiling and that 1000 BTU per pound that you mentioned, you're basically not just increasing the temperature for sake of just making steam, you're sterilizing it. So steam is intrinsically sterile. No worries about anything else when it comes to getting sick. Now, in case of adiabatic, you're managing risk. ASHRAE 170 and CSA 314, they request series of risk layers. And these are not parallel risk layers, these are series. So when it comes to calculating the overall risk of getting sick, you basically have to add the efficiency percentage of each system. I know Kurt mentions that the filters are risk elimination, but filter is a physical device. RO is a physical device. Nothing is 100% efficient. If you assume even 1% deficiency, then it adds up to 5 layers. You have 5% chance of dying, right? So I know I'm making it dramatic because it's a debate, but 5% is a lot when it comes to healthcare.
I think a lot of engineering discussions are missing romance from them, so it's okay.
It's only because, yeah.
Unless you guys are having different conversations than I am.
Because of this reason, because it's not risk elimination, it's risk management. Organizations like WHO do not allow use of adiabatic systems, and that's what the highlighted text says. When there's a need for humidification, use appropriate humidification systems like steam and there's no and, it's only steam, because it's elimination of the risk. Now, if pharma does that, what's the difference with healthcare? I don't see any difference, same sick people, right? So.
All right, I think that's a good chance. You guys wanted to respond to that? Allow.
I'll pass this to Kurt in a second. The one point I would like to make, a lot of
Kurt's revving up over there.
when we see these standards, a lot of the standards are in the process of being updated right now. In the healthcare space in particular, it was the ASHRAE 170 standard that was first updated to allow adiabatics in pursuit of some of the decarbonization goals. We saw the CSA Z3117.2 standard add that in last year's publication as well. So things are changing very rapidly, and I wouldn't be surprised to see these ones change in the near future as well. And Kurt has ideas.
Kurt, you got 20 seconds.
I was just going to say, I think the guys on the steam side don't recognize that we actually cool our buildings too. We have cooling coils, they're everywhere. And in the GTA, you dehumidify in the summer, You've got moisture in that airstream all summer long. And so if you aren't able to manage that risk of moisture in your airstream, don't think you can only do that in the winter and not in the summer. So you've got to have a way to overcome that. And I'll tell you, so that's why we put filtration in where we do to manage that risk as well.
No, it was more than 20
But we don't want to double it, right? So if we have it, we don't need to increase it. So I actually have one more slide to add, just 10 seconds.
No worries,
So,
as long as it's a good slide.
in adding the risk for a series layer system, you have to basically add all the risk. So if we assume that each layer of protection, which there are 5 layers, they have 1%, 2% efficiency rate, it adds up. So basically you might have 10%, 20% or chance of failure in the system.
Alright, I know there's more to be said.
Too much fake news here.
Too much fake news. A statement I did not have on my bingo card for this evening.
It's facts.
Man, if there was a train, I should probably keep it on the rails, but this is more fun. Alright, we've got one last question here. And then at the very end of this, by the way, there will be a Q&A from the audience if there's anything you're looking to ask. But for the isothermal team, when it comes to decarbonizing, why are isothermal systems superior to adiabatic?
Because they just are.
Okay, it's a 4 minutes to respond.
All right, here we go. So first, let's just talk about the power source for all these systems that we do talk about with isothermal. You need to talk primarily about either natural gas or electricity. Now, I want to specifically talk about electricity first, and then we're going to come back to the natural gas. You go find you know what I'm looking for. That one. So with regards to the electricity side of things first, this is what we're just using strictly resistive heat to make our steam, which sounds great. That's 100% efficient, or 99.8, because entropy and second law of thermodynamics and whatnot. However, where that energy comes from matters, and I ask you all to do me a solid when we're talking about electricity and zoom out a little bit. Here in Ontario, which we do have a lot of hydroelectricity, which is extremely carbon friendly, if you don't consider the dams that we have to build to make them. We also have a decent amount of wind, but we also have natural gas power plants. Natural gas power plants, when you talk about the energy efficiency of those, is roughly about 60%. Now, as my friends across the aisle just also mentioned, we're not only talking about Ontario, Canada, we're talking about, a lot of different places. Well, great, because the story gets worse the farther you go. You get to Atlantic Canada is still primarily coal-fired power plants, are approximately 40% efficient. So that 100% electricity adiabatic system there with their gigantic fans that they need to push through their hundreds of filters that they're talking about, which are so important. Well, that can be, yeah, it sounds great that motor is just running off the electricity, super clean, but where that energy comes from matters. And if that energy is not coming from a clean source, what's the point of what we're doing in the first place? And when you think about it, you actually kind of take that side to another part of the conversation. We can actually start talking about gas. And gas is actually where we do get efficient. The natural gas delivery system that we have for usually our steam-fired humidity boilers are about roughly 80% brand new out of the box. Great, but not fantastic. Well, that's where the world of heat recovery can come into these pieces. We talked about the regular required blowdown for those steam boiler systems. Yes, we can heat recovery off of that, and not just feed 40-degree water into our boiler, which will, give us a bit of a thermal shock anyway. Not to mention the fact that when we're heating steam, especially high-pressure steam, we have now a free geothermal well in the stack. Our exhaust becomes an infinite source of energy, provided that we have the infinite need of the humidification, where we can use to do domestic hot water preheat, we can use to do hydronic preheat, we can use to do the feed water preheat, we can do all sorts of things with the heat recovery side of things. And that's where the conversation changes dramatically, where now electricity is the dirtier way to do it when you think about it from a large-scale point of view. And of course, the infrastructure going into making that electricity as well can be a different part of it when it comes into it.
Just 20 more seconds.
No, I'm good. Go ahead and rebut that.
Wow. So, yeah, I've not heard that much misinformation. So let's start with, we're going to put this slide up that talks about how clean our grid is. So we're all here in the GTA. We're talking to a GTA audience, and so local matters to us. That's what we're here to talk about. And in our case, our grid is very clean. And across the country, we are moving towards cleaner sources of a grid, which means we're moving towards electrification. many different ways of electrification, whether it's nuclear, wind, solar, but we're certainly moving towards cleaner grids. So if you're looking to decarbonize, I've never heard of people saying use more natural gas to decarbonize. I think you missed, that was something we used to do in the 90s. And that's really what we were doing back then. We're trying to move towards natural gas away from coal, but I think that's where we realized we've got to move to the next step. And that is moving towards electrification, clean sources of electricity. And that is where adiabatic humidification makes a big difference. Because if you try to do humidification with steam, you're going to use probably 3 to 4 times the amount of energy, if not more, depending on the application. And I work a lot in healthcare, and there's a truth to the fact about heat recovery and how much heat recovery you have, but it's really more expensive. When they talk about heat recovery in steam systems, that capital cost, if you want to try to do it efficiently, is far more expensive than if you just move to adiabatic humidification. So you're going to try to recover all that heat from steam systems, but it just doesn't work out. Thermodynamics of that, I should introduce you guys to the second law, because as soon as you increase the temperature of that steam, and it's that far away from the temperature of the air, you're all going to have irreversible losses. So you can't make that up.
Excellent rebuttal, please. If you want to keep building on the same question that we were asking before, why is adiabatic a superior decarbonization technology?
I know that you guys can't see the slides very well, and it's kind of hard for us to turn our necks this way, but I'm going to let this do the speaking for us here.
You don't need to, it's fake news.
Yeah, nothing but that was true at all anyway, so.
Yeah, debates are a lot easier since you can call things fake news, actually.
There's a slide with 70.
The other thing I'd really like to highlight here too is a lot of the best benefits here in Ontario that we get from adiabatic comes in the shoulder seasons, where we're able to take advantage of the cooling effect to pre-cool the outside air. It allows us to delay the onset or the turning on of our chillers, and really that's an excellent opportunity for decarbonization, that we're taking advantage of the adiabatic systems. Sometimes the year, as they show, January, February, when we're heating at the same time, yes, we're equivalent energy. Once you get to the shoulder seasons, though, that conversation changes entirely. The cooling becomes very beneficial for us. We're not turning our chillers on as early. We're saving overall energy. When you do the math on some of these systems, when we're operating in beneficial cooling mode, you often are running energy efficiency ratios as high as 45. It's a very efficient way to cool the buildings, and any hours where we can have a net benefit on reducing your energy load for the year.
Alrighty, that's a rebuttal from the Isothermal team.
Yep.
I'm glad you brought up that slide about the energy. I mean, when you guys were talking about it, it was really like looking at a sliver, because at the end of the day, when we make steam, we're injecting steam into the air, and it's very easy for it to get absorbed. With an adiabatic system, you're basically throwing in water droplets and expecting them to get reabsorbed. So you need more distance and temperature, which means you have to put that heat that needs to come from somewhere, and that's where the energy is always the same. You can make the argument about the fact, bin hours and all that, we can compare them, but at the end of the day, you have to look at the total energy of the system. And if you're looking at the total energy of the system, you have to look at also the water consumption, right? You have to use an RO system, and there's all major losses that are associated with it. We spent a bunch of time talking about risk management. At the end of the day, we're putting water in the airstream and water in the air handlers, and it's just sitting water, and we always want to try to avoid that. The cost of a mistake there or something not working well is much higher than an isothermal system.
And Mo, I actually just want to expand on that for the audience and say, this is just a general question I'll let you guys respond to as well. What are the risks of water sitting in the systems for those who may not know, or may not familiar?
Well, it's bacteria and you have bacterial growth and stuff like that. So on cooling coils, it's very easy to treat because you just put UV lights. It's sitting water, so it's very easy to kill and maintain that. Because the RO water particles are very corrosive, right? Also, your construction of your air handlers, we make very good units, so we can support that. But you also need a very good unit, otherwise you can have corrosion issues and stuff like that. And also, if that air bypasses your moisture eliminator or whatever it is that you have in the industry, that corrosive air is also traveling into other components that may not be designed with all stainless steel construction to support that, right? So there's a lot of risk that's associated with that. I do know that you guys spoke about updating standards, right? And Z 317 just recently got updated, I'm sure after, heavy debates and stuff like that, but one of the many things that they didn't want to do is make sure that it size with enough distance so you don't have any reabsorption, because at the end of the day, we just don't want sitting water. And an isothermal system is always going to be a lot more efficient because we've got hot steam that so easily gets absorbed into the airstream.
Right, you guys have 30 seconds, and then we're moving on to closing statements.
Yeah, I was going to say, as a manufacturer, put a manufacturer hat on here. Manufacturers go through great lengths to make sure that we don't have standing water in the systems, regardless of if it's steam or isothermal. That's something that's really designed designed to maintain this high level of hygiene. The other thing too, we're talking about building wet sections in air handlers. There's code requirements for how we build drain pans. And as long as we're following our code, we're not having standing water in the air handler. Water in the air handler that's sitting around is a big problem, regardless whether it came from a humidifier or cooling coil or something else. And so, when we're designing the code compliant wet sections, we really don't see this issue.
Alrighty, guys, just for the sake of time here, I'm going to say, call there, we can cover it in our closing statements. Isothermal team, do you have any closing statements? You have about 2.5 minutes to summarize why your technology is the best, why your technology is the worst, etc.
Sure. So thanks so much for sharing all the fake news. So I love that statement. So when it comes to, in my opinion, when it comes to occupant health, we should not optimize for energy efficiency. However, for decarbonization, we have the choice of using electric boiler or use heat pump for steam generation. In a project, we use heat pump for steam generation. And nobody stops us from doing that. When steam is 100% intrinsically sterile, and if we want to decarbonize, why not just choose the source of it? Why are we trying to change the outcome? Patients, occupants would benefit more from steam than from a adiabatic system. And all the 5 layers of combating with Legionella growth is all prone to machine failure and human failure. So, as I said, like as simple as putting salt in a softener in hospitals, sometimes they forget it. It's not like they're afraid of steam. They forget. It's busy environment. It's everything happens all of a sudden, and you forget to do the maintenance. It's not always as per the book, right? So we should not basically put our patients facing that increased risk of failure. Yeah.
All right, if you guys want to add anything on there, you have another minute or so.
There's some we can.
You grabbed that mic so quickly. I think you knew you had done.
I thought I ran out of time, so keep going. So when it comes to decarbonization, we have not just been selling systems of 1800s, right? So there are solutions that keep going. There are solutions that we have continuously. Yes, one more. So when it comes to pressure, one more. When it comes to pressure to steam and centralized generation, there are multiple solutions to decarbonize. And specifically in Europe, there have been a lot of projects doing that. You can actually convert your gas boilers to electric boiler. You can use medium voltage, high voltage electric boiler, and you can use the steam battery using intermittent renewable energy sources to save steam for humidification or any other application. Now, in district systems like hospital, you benefit from shared services. You use the steam for sterilization, for heating, for humidification. So cost of service is divided by 3 and much less.
That was actually a really good time. Alrighty, excellent final statements. Team Adiabatic, why are they wrong and why are you right?
Right, I would say ultimately what we're talking about humidification, that's great. It's great for occupant health, and we're not only talking about healthcare. So if we talk about healthcare, we've got other mitigating elements that we put in there, such as filtration. Not everyone is getting sick from air, from that air. There's bacteria and contaminants everywhere. So you're controlling for many other things in hospitals. Most hospital-acquired infections aren't through the HVAC system, just to be very clear about that. And because we design HVAC systems and all those filtration systems, we want to encourage humidification in many buildings because it's better for occupant health in many different building types, institutional building types, residential building types, and so on and so forth. And in that case, operational cost is the biggest deal. And so if you look, because that's why humidification systems get turned off time and time again, and the most common humidification systems we have today are steam humidification systems, and those are the most common ones that we see turned off. So if we talk about systems that are easy to maintain, easy for facility managers to maintain, and so on and so forth, and technicians to maintain, it's got to be systems that are this simple, and what they used to seeing all the time, a lot of pumps, some very simple water treatment systems that you can get someone to come in and take a look at, and not steam boilers that you have to go and maintain and have expensive, more experienced staff looking at all the time. So ultimately, we're talking about being able to decarbonize, lower our carbon footprint of our steam systems, increase general occupant health across different building types, and that's why if we're going to move forward over here and meet our carbon targets in Canada, as well as improve occupant health and indoor air quality, which is the theme of our ASHRAE president, then we want more humidification systems in buildings, and they've got to be cheaper to operate, and that's where Adiabatic wins hands down.
As long as they're safe.
Hey, this is not for all time.
And maybe just a final thought as well. I mean, the adiabatic systems we're talking about today are light years different than they used to be, going back even 10, 15 years ago. Modern systems are designed to be a lot more user-friendly, a lot more reliable, a lot more self-sustaining, and a lot more accessible. These type of systems really benefit a wide range of buildings, building types. They're designed to be safe. They're designed to alert operators to potential issues and risks and help mitigate them and maintain them. And I really encourage everybody to consider one for your next project.
All right, thanks for the debaters there. We now have a Q&A period, just a couple of 10 minutes. Does anybody have a question? I will hand you a microphone and then just direct it to who you'd ever like to answer. Yes, I see one over here. I'll just raise your hand and I'll come to you if you want to ask a question.
So this question is for the isothermal team. There was a slide up there that was showing the operation costs and how they're actually the same for both adiabatic and isothermal. I just wanted to, I guess, like a simple explanation.
Consumption of operation costs.
Oh, okay, so that's my mistake. Sorry,
No
what was
worries,
that?
and it's only for winter months.
For the winter months? Or no.
One.
That one.
That's right, it was only
Do you mind-
confined
do you
3
mind
months a year,
explaining the
not
slide
6 months, right?
Do you mind explaining the slide again?
Yes, so basically,
Yes, there are 3 months of trauma time, December, January, February, and consider the average temperature, average relative humidity, and assuming 50 Fahrenheit inlet air, and final destination of 22 Celsius, 45% relative humidity on the psychometric chart, both of them land in the same amount of required energy. So in adiabatic case, you have to inject heat to air stream. So through evaporation, it humidifies. In the steam case, you use that amount of energy to boil off and then heat up for the rest of the settlement.
No, sorry, thank you.
All right, anybody else?
I have a quick question. Reza, what's today's date?
I'm at your phone.
April 8th, is that what you said? Oh, so April does exist. Okay, just making sure. Okay.
Thanks so much.
Yeah, one thing I should just add to that is, I mean, when you're thinking about, absorption of the water droplets in the air, the efficiency of that is directly correlated to the temperature, right? So, depending on the type of system that you have, the amount of outside air that you're bringing in, a cold day in April may not be a good day for you to be trying to use that because you need the heat for that to get absorbed, right? So maybe a mixed air system might be a little bit better, but yeah, you definitely have to watch those temperatures, right? Because, if you go and look up regardless of what technology you use and what manufacturer, the fundamentals are always the same, right? Temperature is the biggest driver, and that's why we're trying to keep that air up 70 degrees, 65, 70 degrees, so you can land at, at your 55, right? So, you do have to factor that in. So, the more outside air that you try to introduce in almost colder shoulder months, you may run into issues, and you do have to add the heat back in. I think the message that went with this slide was particularly is, there's no snake oil here, like, the energy's gotta come from somewhere, and it's coming from the air, for the vaporization.
30 seconds for rebuttal, and then the next
You're absolutely right. And so like Reza wanted to pick on healthcare facilities as well. Well-designed healthcare facilities that would have adiabatic humidification have heat recovery chillers. So we've got, someone from a hospital that we're designing right now, and is very proud of the fact that they've got large heat recovery chillers. That is going to be one of their first steps. So that heat that you're talking about we have that available to us, and that's what we can use for heat. And it's more available actually in those shorter systems.
You get one thing to say, and then it's the next question.
No, that's 100%. You can use the same amount of heat recovery and generate steam with a waste heat recovery steam generation heat pump.
Right, and then we talk about cost.
I don't think you understand what one more thing means. All right, Jamie.
Hello, first time caller, long-time listener. So my question is, you spent a lot of time talking about the health impacts and kind of like these worst case scenarios. Are there studies that compare in a controlled setting if you have a steam system compared to an adiabatic system and the actual potential differences in health outcomes for the people in the buildings? It's a generic question to anybody if that exists. And then the other part is there's a lot of discussion about hospitals, but most buildings aren't hospitals. A hospital should be a more sterile environment in general. So that's a two-part question. Are there studies for one? And then if it's a more sterile environment, but now you're not more, I look around, there's lots of bacteria because there's people, COVID taught me I should be scared of people. And I'm just trying to understand, in environments where it's less concerning to have added viral load, it's only a few percent, I'm assuming, if you have some standing water in an HVAC system. Is it actually that large of a
But
concern?
not all of them are lethal, like Legionella. So I know a person who got Legionella. It's not nice. So basically there are lots of viruses, bacteria all over, but there's no Legionella here. So
There's no anything. There's no anything, Steve, is really the point of it. It is completely sterile. So when you're talking about the entire portion of this conversation, I was talking about the health and reproduction of bacteria and molds and fungus, stuff like that. When we're talking about an isothermal system, we don't even have to have that conversation at all, meaning 90% of this conversation we've had up here is moot. Now, when we need to have that conversation to say, well, what about, some other styles, that's really where it comes in. I'll let you boys take it from your side as to how you think your hygienic system is.
I just think, if we're talking about Legionella, and that was brought up, right, the temperatures we're talking about that the water is in an adiabatic system, and what the air temperatures are, is nowhere close to where you have rapid, Legionella, that's not the ideal point. It's much warmer than that. More likely what you're going to see if you've got water sitting in the drain pan of the steam system, that's a little bit warmer, but you're not going to have Legionella. It's not probably going to be the
What temperature do you think it grows in?
It grows at all temperatures, but the rate's much higher. The warmer.
Right. What temperature do you think that is? What temperature do you think is the prime temperature for Legionella?
The risk, it's 110, 1.
Yeah, yes, but it's the temperature we shower at, 105, roughly, yes, yeah. Okay.
Right, so that's not the temperature of the air that we're dealing with right now, right? When we're talking about humidifying, that's not typically what we're talking about, in the healthcare application. And then regular buildings, for sure, it's less of a concern. And with respect to studies, I think I'll let these guys talk about it here and what certifications they have.
I'll actually say, I was going to end that 2 minutes ago, but I was having a lot of fun, so I'll let that one keep going. All right, we have time for one last question. I know you all want to go home, probably. Any last questions here? Yes, let's see one more. Okay, one last question, guys, then I'm going to be calling.
My question is related to the total life cycle of the product. So when we compare two different options, when you say total life cycle, what will be the cost, including capital cost, operating maintenance, utilities, which will be a benefit? Because I know it's not technical, it's not very good medical. I just want an overall view.
So the upfront cost of air handling unit, the cost difference of adiabatic versus steam, it could be huge, and that's for large projects. Now, I appreciate that Kurt mentioned that right humidification needed to be introduced to many more buildings. That's understood. But for base large buildings, the cost difference there is no study or guarantee to show that it's going to pay back. Basically, that's it, double-digit millions, and yeah, so that's a fresh, non-fake news information that. So there's no study. It's right. I haven't found it. If you guys know of any study, there's no.
Generally speaking, with you're going to find a lower first equipment cost with a steam type system. That your initial investment on equipment is at the lower end. It's a little bit cheaper to install. A lot of these tend to be packaged catalog items. Where the costs tend to add up is over the life cycle, where the energy cost remains constant year in, year out. With the adiabatic tank systems, you'll tend to have a higher first cost, and you have some additional costs on the air handlers with the wet sections that you wouldn't typically find in steam. And the key here is having the system applied in an application where there's beneficial cooling. When you have that beneficial cooling and we're able to take advantage of that, now you're essentially getting free humidification for that time of year, and you're typically reducing or offsetting chill-out energy. And that's where the life cycle costs can be very useful in those type of applications.
All right, Mo, go ahead. Kurt can say his piece, and then we'll.
I'll just say.
I said Mo can go first, and then Kurt can go. I have to maintain order. Right?
Kurt, you're getting the last word. I mean, that's a bonus for you. I just want to say just a couple things. I mean, I think both sides here agree that for occupant health, humidification is essential. Doesn't matter what you do, just make sure you do it, right? Because overall, that's the one common thing that we both can agree on. You know, the cost, I get asked this question all the time. And it's such a tough question to answer because it's so site specific. It's like, what are you trying to do? Where are you solving it, right? Are you centralizing? Are you decentralizing? What's your heat source? Or like, you can't answer that question. If you truly want an answer, you have to look at your application specifically and to get you that. And for me or anybody here to tell you just generally that one is better than the other is really tough to say because your building is so unique and it's, you know, we got to talk one-on-one and figure out what's right for you. That's the one approach. And also with, I know, we focus a ton on centralized steam as a source, but don't forget that we also have just atmospheric steam. And you guys, every one of you has one at home. It's called a kettle. You know, you make your tea in the morning or whatever it is. That's essentially what we're doing. We're boiling water. It's very simple to use, very easy to maintain, right? And in the majority of the time, that's basically kind of what you're dealing with, right? So I'll just leave it, you know, don't forget that option because it doesn't have to be centralized. It can also be centralized, and that will help bring the cost down. With
all right, well, you wrap that one up in 4 seconds.
You escaped.
Just the kettle example is a bad idea because you don't boil your kettle in water all day because if you did, it'd be full of gunk in like a few hours, right? Like if you're boiling it all day, 2 weeks later, you can't use your kettle. And I guess, you know what, I'm going to end on that because
Kurt, is this a trick?
It's a line point I wanted to make, but I don't want to get into it.
Kurt will be available for after-hours questions, I guess what you're trying to say. All right, well, I technically lied. I get to ask the last question of the evening, and that is, did you all have a good time tonight? Fantastic. We have 2 excellent teams here. So before you guys all run away, we are going to do the 50-50 after this, so hang tight. But based on a tradition I did last year on a total whim, we're going to do the who won this debate. We're going to do it based on total applause. So if anybody has industry plans here ahead of time, based on the volume of people, I won't name names or look at anybody, that'd be rude. This may be your time to shine or earn your paycheck. So, after such a fantastic debate tonight, who thinks that the Adiabatic team won this debate? And who thinks the Isothermal team won this debate tonight? You have been fantastic. Thank you again to our wonderful debate teams. Let's give them a big round of applause. Okay, 50-50, come up here.